general relativity, but they did have some interesting other.
Well, in order to avoid that this meeting become your group meeting, perhaps you can wait 5 more minutes or something like that, right? Because it's almost like your subgroup meeting.
And it's not,
Oh no, there is people there.
yeah, there are some people there,
Yeah.
but I think that they are mostly.
Yeah.
Who else is important? Meeting?
Uh,
Yeah, maybe the local people.
there, Pipex. Should we get started or should we wait like 5 more minutes?
Charge.
Fernando, thanks for coming. Meeting's over. Congratulations. That was lovely seminar. So yeah.
Thank you. See you next time.
Yeah. There's a brewery around the corner. Shall we?
Yes, right away, right away.
Oh, I'm sorry. There's on the underground here. There is a coffee shop around the corner.
I'm 27.
Oh, perfect. So yeah, perhaps I'll get started like warming up the engine, so to speak. So I first of all would like to say a big thank you to Bibek because he has organized this seminar over the last semesters, and I hope I can do as amazingly as he did. So Bibek, thank you very much for organizing the IQS seminars. And
Give him a round of applause.
yeah, right.
Cristiano,
Okay,
take it over.
Thank you, Vivek. And also, perhaps we can also give a round of applause to Sarah because she's very helpful, and Malina as well.
Yeah.
So yeah. Yeah, with that, we can start. So let me introduce Fernando. I'm reading his CV of the Lattes or platform, so I hope he's up to date. So
Wow.
yeah, he did his PhD in the Federal University of Rio de Janeiro under the supervision of Luiz Davidovich. And then for postdocs, one in the Max Planck Institute and another one in Germany, another one in Freiburg, also in Germany. And then he left to drink good beer in Belgium. And then afterwards, another PhD with, or in the CWI in the Netherlands. And now he is, it's difficult to translate this kind of thing, but he's a associated researcher at the Brazilian Center for Research in Physics, CBPF. And today he will talk about a finite resources description of a measurement process and its implications for the Wigner's friend scenario. Fernando, you have like an hour, I think, right? Yeah, and usually we will, we interrupt you. But yeah, feel free to say no. Questions only to the end. So yeah, floor is all yours. Thanks once again.
Yeah, well, I mean, thank you very much, Chris, and for all of you who are there and people anywhere. I don't know actually where all of you are. So it's great pleasure and honor to give this seminar here. I hope we will have a very nice discussion. I mean, many of the things that I'll be talking about here, I learned from the articles from Matt Leifer's group. So, I mean, of course, all mistakes are mine, all misunderstandings are mine. But I mean, it would be very nice to discuss with you guys. Yeah. So as Chris was saying, so I work in Brazil, so in the Brazilian Center for Physics Research. So it's a research institution in Brazil, and it's in Rio de Janeiro. So it's very close to the beach, and it's a very beautiful place. So despite of the tensions between US and Brazil nowadays, I mean, you are of course very welcome. So if you want to drop by, just drop me a line. I'll be happy to have you here. Yeah. So okay. So the work I will be presenting is this. It's a very recent work. I mean, you see, it's 24. So it's in the archive 24. So it's the end of last year, but we are still making progress on it. So I hope that we can discuss and have some fruitful discussions here. Okay, so let's go. So I mean, I need not convince you that quantum mechanics is one of the greatest achievements ever made by humankind. And this year we are celebrating 100 years of quantum mechanics. And I mean, I tend to believe and I hope that I mean, from this picture, which is there from up to today, I mean, we've learned a lot about quantum mechanics, right? So, I mean, not only conceptually, but also, I mean, the experiments have, uh, I mean, we are controlling quantum systems with much better than at this time, right? So what started, oops, sorry. Yeah. So what started as a theory to describe the smallest scales of energy levels of atoms and subatomic particles, right? So this is the hydrogen atom, which everyone is traumatized with, I suppose. So nowadays we are controlling systems which are as large as this one here. So it's a very recent article by Marcus Arndt and Stefan Gerlich, I'm not sure I pronounced this correctly, from Vienna, where they see quantum interference of this kind of this little metal of 7,000 atoms, right? So it's 107,000 Dalton of mass, right? Which is, I've just checked, it is 10 to minus 19 grams. It's still quite impressive, right? But they see quantum interference, so you can see here, like, so when they displace these, do you actually see my pointer?
Yep. Yep.
Okay. So when they displace these mirror here, they can change the place where they're making measurements, so they can see this interference pattern, right? Even with these very large bulk metals, right? And so in the corner here, so let me just, so they have this scale for macroscopicity. I don't know how they actually measure this. I mean, how this is defined, but what is important is that towards the years, what we see here is that, I mean, we as community have been able to control systems which are way more complex, right? So, and the top of the ladder here, they have their system now, right? So that's this result from this year, right? And bringing it closer to kind of quantum information. So we have this promise that next year we have 1 million qubits by PsiQuantum. I'm not sure if this is still correct, but in any case, I mean, we see also a large increase in the amount of I mean, the control that we have over complex quantum systems going from 2 qubits and during my PhD up to 1 million qubits for next year, right? And of course, that brings, so this technological development and also conceptual developments, I mean, brings back questions which were already there at the very beginning of quantum mechanics. For instance, the transition from quantum to classical, right? And so all these experiments are showing to some extent that quantum mechanics is universal. So we can apply it from the very small scales of atoms and subatomic particles all the way up to very complex systems and it seems that we can go all the way up to detectors and humans and cats, right? And of course now it's a kind of a technological imperative to decide now when to use the unitary dynamics or when to use the collapse dynamics. I mean, we have to decide how to make this transition between quantum and classical, right? So that's the introduction. I mean, the outset of the questions that we are trying to address. I mean, we're trying to address to some extent the measurement problem, but more broadly, or maybe actually this is the problem in the quantum to classical transition, and that's what we are trying to address here. And what I'll be showing you is that to say that if we have finite resources, then these collapse dynamics can actually be seen as sort of a unitary dynamics where you don't have control of all degrees of freedom, which might remind you of the coherence theory. And I'll show you that it's inspired by the coherence theory, but it's sort of different because we will be dealing with closed quantum systems. Okay, so that's just to put the question that we want to address. So here's the outline of the talk. So I will dare to explain you the Wigner's friend scenario, right? I mean, I must say that all I'll be talking about actually it's independent of the Wigner's friend scenario. But that's where the intuition came from, right? So, and then I want to share the intuition that we had with you. And I see that there are many co-authors attending this seminar as well. So it's just to show you how was our process of thinking this problem. And then I'll show you the tools that we are going to use. As I said, so we are going to be dealing with closed quantum systems. And what we are going to be using are very sort of modern tools of equilibration of closed quantum systems, of closed complex systems, if you want. Right? And after showing you the tools, then I'll show you the model of the measurement process that we are suggesting, and especially telling you where the finite resources enters, right? So I mean the aspect of finite resource enters in the measurement process that we are proposing. And then I mean, since I started with Wigner's friend scenario, I'll just go back and try to understand how they can reach an agreement if this finite resource aspect is taken account by Wigner, right? So if he's really trying to describe something which can be called a measurement process, then I mean, this perspective, there is no contradiction, or there is no more disagreement between him and the friend. Okay, and then I draw some conclusions. And as Cristiano said, I mean, please be sure to just interrupt me whenever you have questions. I don't actually see exactly you all, so I mean, just really open the mic and interrupt me if you have any questions. All right, so I'll briefly introduce the way I think about Wigner's friend scenario. So these fun pictures, all these drawings are by ChatGPT. So I mean, it's as most things with ChatGPT, right? So I mean, they look nice, but when you look closely, they don't actually make much sense. So I mean, it's just illustration. You know? Okay, so the scenario that I'll be thinking is this one, right? So we have a spin half particle here, which starts in a superposition plus and minus. So these are the eigenvectors, plus and minus are the eigenvectors of sigma z, right? And the friend has a measurement apparatus which starts at the 0 position, right? And she will be describing the statistics of this measurement, okay? And for her, she'll be just using the collapse dynamics. I mean, actually, she doesn't even need to know quantum mechanics, but she'll just kind of collecting statistics, right? So and the measurement apparatus is set up such that if the state starts at plus, then the apparatus goes to +1, and if it starts at minus, then it goes to minus. And then if you have a superposition like this, so she will measure with probability half, she will measure the outcome +1, and the state of the system and the apparatus will be in the +1. And with probability half, she will also see the -1 outcome, and the system and apparatus will be then in -1. Okay. But Wigner does know quantum mechanics a lot, and he's describing everything in a unitary form, right? So then, since the apparatus is calibrated in the way I said, so plus gives plus here, and minus gives minus here, -1 here, then if this is a unitary, then the modulo of phase that one can choose, I guess. So he ends up with this entangled state for the system and apparatus, right? So it's plus for the system, +1 for the apparatus, superposed with the other possibility, which is minus and -1 for the apparatus. Okay. And up to this point, there is no problem. There's no issue since they are not even talking to each other, right? So I mean, it's no problem for most interpretations to have different assignments. But then there is this other version by Deutsch, in which whenever a an experimental result has been accomplished. So when there is an outcome here, so she switches on this little light here, which does not say that which outcome appeared, but only says that an experiment has been accomplished. Right? And then in this, when the light goes on, what he can do is to open the lab from his friend and make a measurement and and he can measure this observable, which has these two projectors here. So it's measuring on 5+ or in the orthogonal projection, right? So if now he's using his assignment, so to say, then for him with probability 1, he will measure the outcome related to the 5+. And for her, if she's using her description, half of the time she will measure 5+, and half of the time she will measure something which is in the orthogonal projection, right? So, and this is actually a contradiction because we are having two different predictions which lead to two different assignments of probabilities for the same experiment, right? So that's where the contradiction, I mean, the way I understand it, it comes from, right? So, but it has to be realized that for Wigner to actually perform this measurement here, what he has to do is to measure the system and the apparatus. And notice that I'm kind of ignoring the friend which is who is inside of the lab, right? I mean, I don't want to talk about consciousness or anything of the sort. Of course, I could include her in the apparatus here, but I will not do it, just to avoid some issues that I'm not, I mean, that I don't understand very well. Okay. Okay, so as I said, I mean, he has to make this very complex measurement, and so that's the assumption, so that he can actually make this measurement of the spin and apparatus. And most of the articles on the subject, then they say that, well, I mean, this can be done in principle, right? And that's something that really triggers me. I mean, I find this in principle sentence, I find it very, I don't know, kind of almost annoying. I mean, I get really nervous when I read this kind of thing. Because I believe that there is a strong difference between what is said. I mean, when you say this in principle, that's something when you say it in physics, and then when you say it in math. And I'll try to make this clear. So for instance, in a macroscopic system, right, with 10 to 23 degrees of freedom, so a small energy uncertainty of 10 to minus 10 to 22 joules still contains 10 to the 10 to 23 energy levels. So making a very precise measurement on a macroscopic system, it's really impossible with, I mean, the way I think it's really impossible if you have finite resources, right? So this estimate is in this article by Peter Hyman. And there's another way of seeing it, which I learned actually from the article by the group there from Chapman, which is the kind of making the inverse dynamics, right? So instead of Wigner now opening the friend's lab and make this very complicated measurement, what he can possibly do is to actually perform the inverse dynamics. Now, if he now applies the inverse dynamics, well, then in his description, since everything is unitary, he goes back to the initial state, right? So for the system, it's just the initial superposition, and the apparatus is in the initial state of the apparatus. But for her, so if, I mean, assuming that this actually makes sense to reverse her description, then half of the time she would go back to a state which is plus for the spin and 0 for the apparatus, and the other half will be minus for the spin and 0 for the apparatus. Right? And that's a simple measurement that can be done. Now you just measure the spin on a base which is plus, plus minus, and plus minus minus, and then again you reach the same dilemma, right? So for him, for Wigner, this measurement will give the first outcome here with 100% certainty, and for her, half of the time she will see this, and half of the other half she will see the other outcome, right? So it's the same dilemma, but now one could argue that the measurement is much easier to be carried out because it's just measuring one spin. But of course, again, I mean, you have the assumption, which is you can make a very precise reverse of the measurement process, right? And then again, I mean, you see this kind of sentence, this can be done in principle. And that's where we start to think about it, because for us, I mean, at least in my mind, so the other co-authors who are there can speak for themselves, but in my mind, that resembles a lot this this sort of paradox that we have in thermodynamics and statistical mechanics, right? For instance, the Maxwell's-Demond paradox, right? So if one could make very precise measurements, one could extract work from heat, right? So you could split the hot particles to one side and the cold particles to the other side, and you could extract work from heat, right? And when you put the constraints of finite resources, either for the memory of the daemon or in your capability to actually put this this barrier to separate the two halves, whenever you do this, then your kind of paradox sort of dissolves. So the way we are going to understand the measurement process is very akin to thermodynamics, right? So we are going to think the measurement process as an equilibration process. And that's the reason why we start to think on these finite resources aspects of the measurement process, because we are sort of understanding the measurement process. I mean, so this sort of paradox that the Ignorance friend scenario points out, I mean, we see it very much as a discussion about the second law of thermodynamics to some extent. Okay. Okay, so as I said, I mean, our goal here is to describe the measurement process with finite resources, and specifically we are going to describe as an equilibration process. And I should call your attention to articles by the group in Vienna, who are going the same direction. Actually, just last week, they also had an article on this as well. I didn't update it, so that's the first one. So the group by Markus Huber, they are pursuing a very similar line of thinking. And this sentence that I get angry about it, so this in principle sentence, I mean, so what I'll say is that for all practical purpose, I mean, in this perspective of the measurement process, it's going to be irreversible, and therefore, I mean, all these problems sort of vanish. Okay, so this, in principle, it sort of changes to for all practical purposes in physics in the way I understand it. And actually, I think it's more fundamental than that, but we can discuss it later. Okay. So then I'll introduce these tools that we are going to be using. And these are sort of reasonably modern tools, and they relate to the calibration of closed quantum systems. Okay. So we are going to say that an observable is in equilibrium if its expectation value does not change dramatically from its equilibrium value. So that's what's being shown here. So that's from this is by Christian Gogolin. So what we are saying here is the expectation value of the observable A at time t. So you have it here, rho naught is the initial state. And so that's the difference to the equilibrium, the equilibrium value of the observable, of the expectation value. So here is the equilibrium state, right? So that's the equilibrium value for the observable, for the expectation value.
Can I ask a quick question?
Sure, please do.
Wouldn't it be better to say that the probability distribution of the observable is the same as its equilibrium probability distribution? Because you could have a superposition of two very, very widely separated values of the observable that happen to have the equilibrium value as its as the average, and that I wouldn't want to call that equilibrium.
Sure. Yeah, that's a very good point. I think I mean, that's, let's say, first level, so to say. So I guess in 2 slides, I will actually have the equilibrium for the full state. So then I think like all the moments will be considered. So let me go like 2 slides, and then if I don't answer you, then maybe, is it okay?
Yeah.
Okay. So this equilibrium state here is just the time average state. So that's really like it's a fixed point, right? It commutes with the Hamiltonian. So here we're just looking for the expectation value. You correct pointed out. So I mean, what we're going to say is just that. Okay, so let me rephrase. So we are going to say that this value is in equilibrium. I mean, the expectation value is in equilibrium if it doesn't differ most of the times from the equilibrium value, meaning that this here is at 0. So if you think that you have your the precision of your measurement is like a line here. Sorry. Do you still see my? So if the equilibrium, if your precision, if the precision of your experiment is kind of a line here, so for you, most of the times actually it does not change from the equilibrium value, right? Of course, there may be some revivals, but that's, I mean, for a very complex system, this may take like the age of the universe. Okay? And so there are some nice results by Peter Hyman and even before by some other people, and this has been further developed. But so there is this result which says, so here I'm looking at the difference between the expectation value at time t and the equilibrium value, right? And I'm taking the time average. So this here is meaning the time average. So I'm taking the average over all the times. So time going from 0 to infinity, right? And so it can be shown that it is smaller than the operator norm of your observable divided by the effective dimension, which depends on the Hamiltonian and the initial state. So the effective dimension is just the purity of the state in the eigenbasis of the Hamiltonian. Okay, so you see, so here you just take the diagonal elements of rho naught, the initial state, in the eigenbasis of the Hamiltonian. You square them, sum all of them, it's 1/8. So the dimension is 1 over the period. So, yeah. Okay. So you see that if this dimension here is much smaller than the operator norm, so for you, most of the times actually, your system, I mean, the value of your operator has equilibrated. Okay, and maybe that's what you're pointing out. So now I'll be actually talking about the state, right? So here is again, the time average distance between the state at time t, right? So it's the rho naught evolved at time t and the equilibrium state. But here is, I mean, I'm not making norm 1 and how is it called? Trace norm, right? So it's not norm 1 divided by 2, trace norm. But because I'm not optimizing over all P of M's, but I'm optimizing over a given set of P of M's, right? So the idea is, suppose that you're an experimentalist and you have available in your lab a given set of P of M's that you can measure, right? So if this is the case, so then the distance that we are going to be looking at is the maximum among all the difference of probabilities of all these P of M's, right? So you just look at the probability distribution at time t and the probability distribution at time at the equilibrium, and you make the difference, right? So it's just total variation distance for a given P of M, and you maximize over all P of M's. And Sm is the total number of outcomes in the set M, right? So you have all your P of M's. Each P of M may have, I don't know, X outcomes. So then you have X times the number of P of M's. So that's Sm. Okay, so it's a huge number in principle, right? But you can imagine that for a system which is very large, I mean, you cannot make exponentially many measurements. So this number actually, when you compare to this effective dimension, will be very small. And then for you, for all practical purposes, and in my point of view, in principle, I mean, there is no difference between the state at time t and the equilibrium state. So here I'd say that we are looking for all the moments. Did I answer your question? I'm not sure.
Yes.
Yeah. Okay. Okay, so these are actually the only two tools that the only new results, at least they were new to me. Actually, I learned about them from Thiago, who is attending the talk as well. Okay, so now with that, I can show you what is, what we are suggesting as the measurement process, including finite resources. Okay, so as you probably realize, the finite resources enters in these results that I show you, because we are assuming that you don't have infinite precision, and therefore you don't actually see the fluctuations of your expectation value, and also you don't have access to exponentially many POVMs, and therefore you don't actually see the difference between the equilibrium state and the state that you have over the time t. Okay. Okay, so that's the setup. So as before, we have the system. So it's going to be a spin half particle. So it's a qubit, which starts in a pure state, in a superposition of plus and minus, right? And the apparatus, then we are going to describe it as a d-dimensional quantum system, right? And we are going to split it in 3 subspaces, right? So it's a direct sum of a subspace which will be connected with the +1 outcome, another subspace which is going to be connected with the 0 outcome, and the other one which is going to be connected to the -1 outcome. Okay, and so for simplicity, what we are going to assume is that the dimension of age +1 and dimension of age -1 are both equal, and we are going to call them D1, and the dimension of age naught will be D0. And it's maybe a bit just for technical reasons, but so what we want is that the dimension of like D1 to be much bigger than D0, such that, speaking in very loose terms, so whenever the information goes from 0 to -1 or 0 to +1, it doesn't come back, right? So dimension of D1 of age +1 and age -1 is so big that whatever. So whenever the information goes in there, it doesn't come back. So that's sort of the intuition. And we make it such that D0 over D1 goes to 0, but in a polynomial way with 1 over D, right? And D is the dimension of the total system, total apparatus, sorry. And the reason is that, we have to be able to prepare the initial state, right? So if it was exponentially small, then we wouldn't be able actually to not even start the apparatus in the 0 position. So that's the way just to be sure that we can start everything. Okay, so the initial state then will be this pure state for the spin. And then since the only thing that we know is that the apparatus starts at position 0, so what we are going to do is to assume that it starts at the microcanonical ensemble for this subspace, right? So it's the identity over the dimension of the subspace. Okay, so that's what we are going to take as the initial state. Okay. And now the Hamiltonian is the expected Hamiltonian, so to say, right? So it's sort of a C0-like Hamiltonian. So if the spin is in the plus state, so we want that whatever is in the 0 subspace goes to the +1 subspace, right? So that's this Hamiltonian here, which connects the 0 subspace with the +1 subspace and nothing on the -1 subspace. And if the spin is in the minus state, then it's the opposite. So it goes from the 0 to the -1 subspace, and it doesn't touch the +1 subspace. Okay? So that's the construction. And so we want to make this independent of the details of the Hamiltonian. The reason is exactly because we want to have finite resources. So we don't want to have to characterize the Hamiltonian in all its details. So what we are going to do, actually, we are going to sample these Hamiltonians from the Gaussian unitary ensemble. And okay, so I actually forgot to mention that. So these results that I showed you before, so these equilibration results, there are some new results that go beyond these here, but the results that I showed you they require the Hamiltonians to have non-degenerate levels and not even non-degenerate gaps. Okay, so beside the point that we don't want to, together with the point that we don't want to have full control of the Hamiltonian, and therefore we are sampling them from the GUE ensemble. I mean, these also directly gives us the fact that, I mean, we don't have degenerate levels nor degenerate gaps. Okay, so we are going to sample this Hamiltonian from the GUE ensemble. Okay, and that's a very complicated Hamiltonian, I mean, but it's sampled and the details will not be important. Okay, and all the results that I will be showing you, they cannot depend on the details of the Hamiltonian. Okay, because exactly that's the finite precision point that we are introducing here. And I should point out that's maybe the main difference with the decoherence process, right? So in the decoherence program, one usually assumes to know all the Hamiltonians. I mean, the interaction between the system, the apparatus, and an environment. You know the Hamiltonian of everything, and then just afterwards, you remember that actually you didn't have control of the degrees of freedom of the environment, and then you trace that out, right? So here we are saying that we don't have any environment, but we don't know exactly the Hamiltonian that connects the system and the apparatus. So that's our way of including these finite precisions from the very outset. Okay. Okay, so that's the first result. I didn't start my clock. Chris, how much time do I have? And I'm
Half an hour.
half an hour. Okay, that's perfect. Just because I didn't start it, so now I'll just start counting from now. Sorry. Okay, so that's the first result that we have. It's really like just I mean, we just have to use these results for equilibration of expectation values. And the expectation value that we're going to be looking at is the projectors of measuring in a given subspace, right? So if you use these results that I showed you to the projectors to measure in the -1 subspace or the 0 subspace and +1 subspace, what we can show is that the probability time t given a Hamiltonian does not differ the equilibrium probability for the same outcome, right? So most of the times, actually, this difference here is very small. And so the bound here is 1 over this d0 plus d1. So if these dimensions increase, this is very small. So you can actually say that the probability at time t does not differ most of the times from the equilibrium probability. Okay. So as I said, so the equilibrium probability is just the probability at the equilibrium state. Okay. So that's the first result. But as I've just said to you that, I mean, my results cannot depend on the Hamiltonian, and this is for a fixed Hamiltonian, right? So what we do then is we sample these Hamiltonians from the GUE ensemble. And what we can show is that the probability, the equilibrium probability of a given outcome does not differ too much from the average equilibrium probability, right? So the probability for this difference here being bigger than delta decays with 1 over delta square and also has these dimensions here. So if d0 and d1 are very large, you see that this is going to 0, and then your equilibrium probability actually does not differ too much from the average equilibrium probability, so the typical value. So there is a typicality effect here. So your equilibrium probability actually does not depend too much on the Hamiltonian. Is there a question? I heard something. No. Okay, so I'll just continue then. And the nice thing about these average equilibrium probabilities is actually that we can calculate them analytically, right? And it's pretty much what you would expect, I suppose. So the probability of measuring, so the average equilibrium probability of measuring plus or minus 1 is just C plus minus modulus square times this factor here, which depends only on the dimensions. And then you see that if d1 is much bigger than d0, this goes to 1, and that's your textbook probability. And for the 0, sorry, it's the same thing. I mean, you can also calculate it, but then you see that if D1 and D naught goes to infinity with D1 much bigger than D naught, that actually goes to 0. Okay. So putting all this together, for large apparatus, and most of the times, what we have is the following. So it's this chain, which is kind of Chris is much more kind of formal than I am. So I like to wave my hands and make bold statements sometimes. So the probability for a given Hamiltonian at time t does not differ too much from the average probability for that given Hamiltonian. But this
For
probability
most of the times.
for most of the times, for large apparatus, all
Yeah.
these included in the pack, in the package. Yeah. And this here is not too different from the average equilibrium probability. And the average equilibrium probability, actually, we can calculate, is just this here. And if the dimension is very large in the way I said it, then they actually give you the textbook result. Okay. And the same for the zero outcome. So the zero outcome, I mean, for a given Hamiltonian, does not differ too much from the equilibrium value, and this equilibrium value does not differ too much from the average equilibrium value, and this equilibrium value goes to 0 in the limit of large dimension. Okay. And okay, so maybe just to, I'm not sure what's the definition of your screen there, but I hope you can see it. So here, so it's just kind of numerics I did. So choosing different dimensions here. So here is dimension. So D naught will be always 2, and I'll just increase D1. Here, what I'm doing is I'm just choosing 3 random instances of these Hamiltonians, right? And plotting the equilibrium value for the probabilities and the evolution of the probabilities over time, right? So you see if dimensions are small, you see all these kind of oscillation patterns, and you see that the equilibrium values, which are these, so here's the equilibrium value for the probability -1. I started, I think, with, yeah, superposition of minus and +1. I don't exactly remember the coefficients, but it has more minus than 1. So you see that these lines here, these equilibrium lines, they are different, right? But then if you keep increasing these dimensions, so I'm just increasing the 1, you see that they start to converge. And actually, here is the probability of 0 in black, right? And then you see that it starts to go down, go down, go down. And for dimensions which are not that big, actually, dimension 2 here and dimension 6, 3, 4, D1, and you see that, I mean, all the equilibrium values are pretty much on the top of the one on the top of the other, of course, for this scale of the plot, right? And the oscillations are very much close to the equilibrium value, and this is true also for all the outcomes. Okay, so I'm just kind of, it's just an illustration of the analytical results that I've just shown you.
Fernando.
Yeah.
Yeah, I have a question. It's not the usual questions. It's not the usual question that I always pose to you, but I suppose that when you increase, when the dimension of your apparatus, of your measurement thing gets bigger, gets larger and larger, since you are kind of drawing randomly, Gaussianly, right, from the, in your soup of Hamiltonians, there is a concentration effect, right? So you're not looking at the most general Hamiltonian that you can get to begin with. And when your dimension gets larger, you're reducing, because of concentration effects, right, I suppose, you're concentrating the sets of Hamiltonians that you're dealing with, right? So can you, could you, or did you think of characterizing this set of Hamiltonians that your result is valid for?
Yeah, I mean, okay, so let me address the first
Because I mean,
comment.
concentration is inescapable, right?
Exactly, yeah. So, and it's actually desirable to some extent here, right? So exactly the point that we don't want to, I mean, depend on the details of the Hamiltonian. So, I mean, this concentration tells you that most of them will behave the same way. That's what's being shown in these plots, right? So whatever you, I mean, I guess, I mean, Chadwick was also criticizing that.
Yeah, it's
So
random,
when you
not
make
uniform, right? It
say
might
what?
be the case that it's random, but it's not uniform.
It is uniform.
No, it's not,
Uniform
because
in
we
this
have to
in this
concentrate
measure.
on- Suppose that you're in this
No,
sphere,
no,
right?
no.
That's the kind of the hard measure, right? So if your concentration, yeah, so you're only look to the equator of this sphere.
Yeah, but okay, take care. No? You are the mathematician, so it's not me. But so we are so we are sampling uniformly, right? So I mean, just think on the hard measure. So we are sampling on the hyperdimensional sphere, right? And even sampling uniformly, the volume concentrates around the equator. Right?
Yeah, exactly.
It is because you are actually sampling uniformly. I
Yeah.
mean, it's not because, but I mean, you are sampling uniformly and still concentrates. So I mean,
Yes,
that's
exactly.
exactly what we are doing here. So we are sampling uniformly,
Yeah,
but
but
then there is a
that's good for your,
concentration.
that's good for your results. That's clear.
Yeah.
But the thing that I'm saying is that you're getting rid of, you're throwing away a lot of Hamiltonians as well, right?
Sure.
And perhaps that's the Hamiltonians that are important or like physically relevant, because in principle you're concentrating, that's fine, but it's in principle as well.
Yeah, I mean that's it's a good criticism, and we've been receiving it a lot. But yeah, so I mean, as I was saying, I mean, Charles was saying, so okay, so I mean, when I make I mean, when experimentalists design a measurement apparatus, I mean, they don't do it at random, right? I mean, they
Exactly, yeah.
supposedly know what they are doing. That's true, hopefully. But what I'm saying is that the details are not important. And I mean, okay, so now I'll tell you like a sort of a feeling, and it's a bit more than a feeling, but I mean, if I have Hamiltonians which are in a different ensemble, so let's say Hamiltonians which are band diagonal, right, which are more physically reasonable. Okay, so I don't have results, but I would have, I mean, not put my hand on fire, but I guess that everything kind of follows. It's really strong. It's a matter of the dimensions more than anything, right? So I mean, if of course there are Hamiltonians that these will not work, but this, I mean, my point is that these Hamiltonians are not good measurement apparatus Hamiltonians.
Mhm, mhm.
But of course, I mean, of course, I can construct Hamiltonians that none of these will work.
Yeah,
I mean,
sure, absolutely.
it's
Yeah.
much easier to do that than to actually do a Hamiltonian that works.
Yeah, thank you.
Yeah, no, thank you.
May I ask a question too?
Sure,
Could you please tell a little bit more about the black curve?
the black curve.
Yeah.
Anything specific or?
Yeah, because
Sure.
it is going down, and what
Yeah.
is the physics behind it?
Yeah, sure. So the black curve is related to the probability of measuring the zero outcome, right? So the zero outcome actually is an outcome which, I mean, you should not observe, right? Because you only have the superposition is plus minus, right? So you are supposed to see only the outcome +1 and -1. But since we are in finite dimensions, there is still the possibility of actually measuring zero, right? Which is the initial state of the apparatus here.
Okay.
So what we would expect is that this probability goes to zero. So that's why it's always going down, right? So and this here is because the dimension of D1 is much bigger than the dimension of D1 is much bigger than D0, right? So dimension of the +1 and -1 subspaces is much bigger than the D0. Although, I mean, we can make it both of them increasing, but it has to scale such that it goes to zero in a polynomial way, right? So that's the point. So it's just that, as I said, like waving my hands, the information about the apparatus, which we know it starts at zero because by construction, so we took out of the box, so it's pointing towards zero. It has to go to -1 if the state was minus. I mean, thinking a bit classically here, but okay. And it has to go to +1 if it wasn't +1, right? And the zero outcome should not show up. Like, I'm not sure. Did I answer you? I'm not
Yes,
sure.
thank you.
Okay. And that's what you're seeing here. So it goes to zero. Although here it's kind of substantial, so the dimensions are not high enough. All right, so that was for the calibration of observables. So want to address the other point, which is the calibration for the state, right? And again, so there is no way for me to know what is actually the state at time t, because this would imply that I know with infinite precision the Hamiltonian of this very complicated macroscopic system, right? So that's the assumption here. And that's where, as I already pointed out, is where we differ from the usual decoherence program, right? So the lack of knowledge here is built in the model, right? So it's not something that we put afterwards to get what we want. Okay, and again, so my results cannot depend on the Hamiltonian. And then the construction is pretty much the same, right? So what we show is that for a fixed Hamiltonian and a given set of P of M's, right? So the distance between your state at time t to your equilibration time, most of the times is not too big. And it's not too big because if the number of outcomes of your P of M's, of all your P of M's, does not increase faster than the square root of the sum of the dimensions here, then sorry, then you won't be able to distinguish between these states, right? And that's what mostly happens in experiments, right? So if you were to characterize something which is macroscopic, I mean, you have a handful of observables, but the dimensions are ridiculous, right? So these will be very close to zero. So most of the times you actually have no hope to distinguish between these states, right? And then again, I mean, as I was saying, I mean, this cannot depend on the Hamiltonian. So what we do is, again, we sample the Hamiltonian, and what we show is that the probability for the distance, and here we are using distance, Hilbert-Schmidt distance, the distance for the equilibrium value for a given Hamiltonian to the average equilibrium, for the average equilibrium state is not too big, right? So, and so it does not differ from the average distance too much. So the probability for it to be different from the average distance by something which is bigger than delta actually decays exponentially with delta square and the naught square. So you see that if dimensions are large, so here the naught only enters, but then this goes to zero very quickly. And this average distance, so it's calculated down here, right? So that's we can bound by this quantity here, which goes like 1 over d naught times d1. So this goes to zero. So the average distance goes to zero. So, and then the probability for the equilibrium state be further away by a value delta from the average equilibrium state decays exponentially, right? So then again, it's the same chain of reasoning, right? So we bound for a given Hamiltonian, and then we bound using typicality results for average Hamiltonians. And here's I mean, just to show you the concentration for the same values of dimensions that we had before. So here is just the histograms of the distances here. So the distance between the equilibrium state for a given Hamiltonian to the average equilibrium Hamiltonian. So I just sample a bunch of Hamiltonians and calculate this distance. And you see that if the dimensions are small, then I mean, you have kind of something which is spread. Notice that it's already quite small, but if you keep increasing the dimension, then it gets concentrated. So that's the typicality result that Chris was mentioning. Okay. And then again, I mean, so we can calculate the average state, right? So the average equilibrium state, and again, it's exactly what you would expect, right? So I mean, I always joke that, I mean, we can actually, I mean, guess this here, and I did guess this result, modulo this factor plus 1 here, which I was mistaken, but Raul, my collaborator, found it. So, but it's pretty much what you would expect. So if with probability, which depends on C plus modulus square, so the spin will be in the plus state, and the apparatus will be in the microcanonical ensemble in the plus 1 subspace, and then there is these factors here, which also appeared in the probabilities, right? And for the minus is the same thing, so it's mods square of C minus with the minus in the spin and the microcanonical in the -1 subspace with these factors here. And on the 0 subspace, then we have this mixed state here, which is C plus mod square with the plus and C minus mod square with the minus, and still the microcanonical in the 0 subspace, right? So, and I should point out here that, I mean, here we only made averages, right? So we made the average over time, and we made average over Hamiltonians, right? So we didn't take any trace, anything, right? So the evolution from the pure state, if you wanted, so if you had started with a pure state to a mixed state, comes only because we are assuming that we do not know in detail the Hamiltonian, right? So there is no, I mean, we didn't use anything but averages here, okay? This sort of emerges. And of course, for large apparatus, then you get your textbook result, right? Which is just mod C plus mod square on the plus part and C minus mod square on the minus part. All this 0 component goes away, and all these dimensional factors go away, right? So this is to say that this result which we obtain by a collapse dynamics actually can be seen as the evolution, the unitary evolution, but now unitary between quotation marks in the sense that we are taking average over Hamiltonians, and therefore it's not exactly unitary, right? But it's kind of solving Schrödinger equation, if you want, like on average, okay? So collapse is a very effective way of doing these very complicated calculations. And just to, like, the last point that I want to make on this model is that, I mean, if you're talking about measurement, then, I mean, when you measure, you want these results to stay there, right? So if you were to measure afterwards, then this has to stay, you have to obtain the same outcome. And of course, if you have the outcome +1, you just update your description to this state here. And this state, if you plug in back in our Hamiltonian, then you might think that, well, it starts to go back to 0. It is true, but I mean, if dimensions are very large, then actually it's quasi-stationary, right? So they stay there, basically, right? So for all practical purpose, and therefore in principle, they stay there. So all these states are stationary, right? For large dimensions. And here's the same thing for all the others. So, okay, so just to go back to Wegener and his friend, and then I'll wrap up. So I'd say that if Wegener is actually accepting that he does not have full knowledge of the measurement process in the sense that he cannot know all the details of the Hamiltonian, then he would reach exactly the same conclusion as his friend who's performing this collapse. I mean, who is describing the experiment just by statistics or by the collapse dynamics, right? And here, what we have here is just like for a single run, but you can think that this +1 here is just a vector in the plus subspace, and same thing for the -1. Then on average, actually, what she would say if she were to use quantum mechanics is exactly what Wegener would say for each part of for each outcome, right? So in this sense, I would claim that there is no contradiction if we are assuming finite resources, which I think it's a reasonable thing to do. Okay, just to conclude, so that's Wegener and Heisenberg. I always say that I'm not sure whether they were friends or not, but okay, possibly a friend. So in conclusion, so what we did was to introduce this measurement process that model that takes in account the finite precision when describing a macroscopic system, right? So we get the results, like the textbook results for large apparatus and for large times, right? For most of the times and for large apparatus. And the collapse dynamics sort of emerges from the unitary dynamics if you average over these Hamiltonians. And as we discussed, I mean, I believe that you can make more physically reasonable averages, and the results will be the same actually. And by doing this, although it's not the center point of our result, I mean, we show that there is no sort of paradox in this Wigner scenario, Wigner's friend scenario. Just to wrap up, then, so these are the authors of the article. Some of them are here attending this talk. Gabriel, who is a professor in Pernambuco, it's in the northeast of Brazil. Pedro also is a professor in Bahia now. Thiago de Oliveira, who is a professor here in Rio as well, who is here. And Paola is now in South Africa. She was a postdoc here with Raul, and Raul is my collaborator here at CBPF. And I should say that, okay, so that's the quantum information group. That's our formation. So Mariana, João, and Mario are, okay, so Mariana and João are master students and Mario is a PhD student. So Raul and I, we are the heads of the group. And Alfredo Zor is our guru, so to say. So he's retired, but still it's a great source of knowledge. And so here's the people working on quantum science and technologies at CBTEP. So we have a strong team working on experimental physics and various systems. So from quantum key distribution across metropolitan network here in Rio up to superconducting quantum computers and sensors, quantum sensors with NV centers, and all the usual traditional stuff of quantum technologies, right? And so we are 4 theoreticians and all the rest are experimentalists. And that's it. So I thank you very much for your attention, and I hope to discuss more with you.
Yeah, Fernando, thank you very much for your talk. We have time for questions if people have them. So questions, what are your questions? So there is a question from here and then one question from the audience. Yeah, Andrew.
I'll go last.
Yeah, I can, Andrew, please.
Yeah, thank you, Fernando, for the very nice talk. So if I understand correctly, you then, if you have a meter that's small or a device that is not a macroscopic, but let's say a mesoscopic device or even a microscopic device, according to your model, then do you predict deviations from the Born rule?
I wouldn't say that. It's just that I wouldn't predict any deviation from Bohr's rule, right? So it's just like what Bohr rule would tell you is actually this term here, which depends on the dimension. I'm just saying that when you do have a macroscopic system as the measurement apparatus, then you get the value that you would expect, right? So I mean, Bohr's rule would give you exactly this value here if you were to consider the dimension of your apparatus.
Real measurement devices sometimes fail to click, and that's basically what that is. It's like the measurement device fails to go off, it stays in the 0 state.
Sorry, I'm not sure this. I couldn't hear you properly.
I'm just saying, like, a real measurement device that has finite degrees of freedom sometimes fails to work, right? So sometimes, like, you will get losses if you're measuring photons, for instance. And so staying in the 0 state is effectively modeling the realistic case where the detector fails to click.
Yeah, it's possible. Yeah. Yeah, thank you. Yeah, that's a very good way of thinking, I suppose.
Yeah, but Andrew doesn't look so convinced.
So I'm just saying that if I had a textbook result, I would just get the C+ squared and the C- squared and not get the other term. And so I'm just trying to understand where the corrections come from. So you're saying that if I had a more detailed modeling of the device and applied usual projection, I would get the D+1 and so on from that analysis. Is that correct?
Yeah, that's exactly what I did actually. I mean, so here what I did was this, right? So these values here, so let me go back actually one more. So this here is exactly Bohr's rule, right? So this here is the expectation value of the projector on one of the subspace for the equilibrium state, right? And this is the value that you would actually get. But what I'm saying is that if you were to use the collapse results, right? So the collapse postulates, then you would get only C plus mod square of it, right? But if you're now making, but this, I mean, my point is you are only sort of allowed to do that, to use this collapse prescription, if you're actually making a measurement. And for you to actually be making a measurement, you do need something which is macroscopic in this sense, right? So that's what I'm trying to say. And then these factors which depend on dimension, they will just kind of go away. Not sure.
But why can't I make my detector smaller though?
Well, because then, I mean, what would happen is these kind of things, right? So you would get, I mean, the information, so to say, would go back and forth from your system to the environment, to the apparatus, and back to the system and back to the apparatus. I mean, it's not a measurement process, right? So that's what I'm trying to say. So it's sort of, then it is reversible, right? So if you have one spin measuring another spin, so to say, by some given interaction, then I mean this is not exactly making a measurement process, right? Remember that here we have the interaction on all the time, right? So both of them are interacting all the time, and what we are seeing here is actually an equilibration of a dynamics, although it's closed. It's a closed dynamics, but for you, I mean, for you, you actually see this as an equilibrated value.
Yeah, we have a question from the audience. Yeah,
Okay.
go ahead.
Okay. Do you hear me?
Yes.
Okay. First of all, hello to everybody, and I'm grateful to Andrew since I can join this seminar, and thank you for the nice talk. And my question is, maybe I can formulate or a little bit how I understand this, and then I ask my question. So it seems to me like you try to consider the machinery of equivalence between averaging over time in quantum mechanics and averaging over ensemble. So in the sense that you have quantum system which interacts with apparatus to degree which you don't know exactly, just because of many degrees of freedom and so on. But you know in principle, the equilibrium result, say, which you could obtain. Well, and you claim that, and it's true that experimentalist doesn't have enough time to perform averaging over time, and that causes as well as uncertainty in the details of your Hamiltonian, and as well as uncertainties in the number of degrees of freedom of your apparatus, and the lack of time actually to do the measurement. This causes this strong fluctuation on your graph. And to avoid this, you just saying that you compensate time evolution that you lack to average over time by the number of degrees of freedom, by the number of tiny weak measurement which all together result in the macroscopic measurement, in projective measurement, which gives you at the end the equilibrium value. And in that sense, it's interesting from which number of degrees of freedom of your apparatus actually this projective measurement starts. Because if otherwise, if you don't have enough degrees of freedom of your apparatus, then this picture of equivalence between averaging over time and averaging over ensemble breaks down. So it's interesting from which number of degrees of freedom our usual picture of quantum mechanical projective measurement starts to realize. So that's my point, comments, and questions. So on. It's interesting what you think about this. Thank you.
Yeah, sure. Thank you. Thank you very much for the question. It's a great point. I mean, here we are not making a quantitative prediction, so to say, right? So what okay, so I mean, I can, so for instance, here in these pictures, right? So, I mean, I'm just increasing dimension and sampling over the Hamiltons, right? What maybe would be nice to do is to have some perturbation on the Hamiltonian, right? And control this perturbation depending on the dimension that I'm sampling these Hamiltonians, right? And these would allow me to say, okay, so if in this dimension your imprecision of the coupling constants on the Hamiltonian is that big, then it will look to you as if it was a measurement process, right? So what I'm trying to say is like, if I have this 1 million, 1 million quantum computer, and I do have control of all of them, then everything will go kind of as planned, so to say, like unitarily, right? But if at some point I don't have control, fine control of these degrees of freedom, then these will start to look for you as a measurement process, right? So I guess what I mean, I cannot actually give you a number, right? But what one could in principle do is this, right? So just have perturbations on the coupling constants, for instance, and see how does that translate on the dynamics, right? But for the moment, what we are doing is a very, let's say, a very rough thing, right? So we're just really sampling all these Hamiltonians, and all the details are kind of washed out, right? But in principle, I could, and I think it's a very good thing to do, and to give precise numbers comparing the precision that I have with the dynamics that I get, right? So, but this could be done, but I haven't.
And related to this maybe. So if is there a certain freedom in the number of degrees of freedom for each value of what you call effective dimensionality? So like when the same value of effective dimensionality can be produced by different numbers of actual degrees of freedom of your apparatus, or it's like very very strongly fixed, like you cannot
Right.
obtain. So do you have a freedom in this?
Sure. Okay, so the effective dimension here actually is defined here, right? So it depends on the initial state and the Hamiltonian that we have, right? And these bounds that we have, in all of them, we use that rho naught is this state that I showed you, which is like pure state on the system and the microcanonical on the apparatus. And by doing this, so what we guarantee is that many states on the Hamiltonian or on the eigenbasis will be populated, right? And I mean, I guess we could change this, but then the bounds would probably change here. So these the dependencies here, they would be maybe different, right? So this, of course, I mean, small change. So that's one criticism that we also got, that this initial state here is not a full rank state. But I mean, we can put like epsilon identities on both sides and make it full rank. And then these values would probably not change dramatically. But I guess if you were to choose a different class of initial states, I guess they might change. Actually, these ones not. So, I mean, if everything is pure, even if the initial state is pure, this here would be still the same. But for these bounds on the distances, this may be more complicated if the initial states were pure, because I mean here is not a linear function, so it's a bit more complicated. But
Fernando, we have a question here
Yeah.
from the room. Matt has a question or comment, or I don't know.
I have I'm trying to be very quick because we're low on time, but I have a couple of comments and a question. First comment is Wigner's friend is not Heisenberg, it's definitely Dirac, because Dirac married Wigner's sister, and
Okay.
they had to be very good friends. Also, Dirac did not
Wow.
like to interact with his environment at all, so he would be a very good candidate for putting in the box. That's a silly comment. My second comment
That's nice.
is
That's
really,
nice.
I think we said this in our review paper at some point, at least in one of the drafts. I totally agree with the technical results that you have here, and that certainly for all practical purposes, a measurement is irreversible, and Wigner and his friend will end up agreeing that you should perform the collapse in the case of a measurement. But what we said in the paper was that when you're concerned with the interpretation of quantum mechanics, you're precisely concerned with all impractical purposes, right? Because certainly something like the EPR experiment was considered a thought experiment that could never be done at the time it was proposed. And even if that were the case, you still have to deal with, you have to say what will happen in even incredibly contrived and improbable situations. That's the goal of an interpretation, is to tell you what will happen in any physically possible case. So following on from that, I also want to say, the question is really here sort of what really constitutes a measurement, because certainly a realistic measurement device like we have now, those kind of things, they tend to behave in this sort of way. But people are proposing things like doing the Wigner's friend experiment on a quantum computer with an AGI, a general artificial intelligence, and there you can say, well, what I really need for a measurement interaction is just something like a CNOT gate on a quantum computer. And if I chain a lot of CNOT gates together, I can get a large amount of decoherence, but that's all very, very fine controlled, right? So the question is, are you claiming, or would you claim that that does not constitute a measurement, that does not constitute a Wigner's friend experiment, or that it does? Because if it does, then obviously this is not really going to address the sort of paradoxes there.
You mean the experiment with the artificial intelligence?
Yeah, so artificial intelligence on a quantum computer, run it in superposition. All that the friend has to do to make a measurement, in principle, or Wigner has to do, is to do a bunch of CNOT gates, right? So you're measuring this spin. It's basically a CNOT gate between a large number of qubits. Now, if it's a sort of a polynomially large number of qubits, it's still efficient to undo all of those CNOT gates and then make the kind of reversal that you were talking about earlier, right? So the question is, in order for your work to resolve the paradox, you would have to make a claim that that is not a valid instantiation of a measurement. Also, you'd have to address, so there has been some work on the practical implementation of this. So for example, I think Cavalcanti, Reifel, and Wiseman have a paper on how what resources would you need to actually implement this experiment on a quantum computer in the way that I suggest? Like how large would the quantum computer have to be? What kind of decoherence times could you deal with, and things like that. And their estimates show that if we have universal scalable quantum computing, and if AGI is possible with an efficient algorithm, then you ought to be able to do this at some point in the future, like according to their resource estimates. So, you know, again, one has to say, not only does the typical measurements that we do in everyday life with actual detectors in the real world, you know, you can't do Vignes friend with that. I think we all sort of agree that you'd need a Maxwell's table for that. You have to also argue that for some reason, these kind of implementations do not constitute a valid implementation of Vignes friend. I think that's the harder thing to argue.
I see. Yeah, I mean, I must say that I don't know this article, I mean, in detail. As I said, I mean, Venus friend here is, for me, is just more like a motivational thing. But I'd say that in these scenarios, I guess I would, okay, so without reading and just from what you said, I would be on the side that this actually does not constitute exactly a measurement process indeed. I'd say that even if you're trying to make this kind of chain of CNOTs, I mean, eventually, I mean, if you're actually performing these CNOTs, I mean, if you chain many of them, maybe polynomial many will be not enough. But if you're making polynomially many of them, well, let's see. Okay, so if you're making actually exponentially of them, it's no longer reversible, right? So because I mean all the errors that enters in each one of them, they will just kind of creep in, and very quickly you lose everything. But that's okay. But if you're making polynomially many, I'm not so sure about anymore. But I'm not sure this would constitute a measurement indeed. Yeah, I think I would lean to this direction, but I'm not so sure about it now.
I mean, I think the issue here is that I don't think anybody disagrees that what you're talking about here is sufficient for a measurement. The question is, what's the necessary condition for a measurement to occur? And nobody agrees on that. That's the difficulty that we have.
Yeah, we have like
Yeah.
the last
Yeah.
question here. Yeah, and then we can wrap it up.
Thank you for the nice talk. I have a question, like even for actual detectors, what guarantees that D0 is much smaller than D1?
Well, I mean, I think this has to be made like in the design of the apparatus, right? So that's kind of construction thing. Right? So it's really.
I mean, a common design for
Maybe.
detectors is that the ready state is some kind of thermodynamic metastable state, and then when you have the measurement interaction, it causes the thing to go into one of two equilibrium states. Yeah, so the fact that it has a much smaller dimension is going to be because it's not actually an equilibrium state. It's like some lower entropy state. So you expect it to be associated with the Hilbert space at lower limit. That's for instance how many practical kinds of detectors actually work. Not every single detector, but it's cool.
In principle, it's possible to design a detector that D0 is comparative to D1 or even larger than D1.
Again, it depends what you're prepared to call a measurement.
Yeah, I
right?
mean, in principle, yes, but
In principle,
yeah,
it's possible.
but is that a measure?
Still a measurement.
Yeah.
Yeah, that's the point. Yeah.
You could swap the labels here and say that you're detecting 0, and
Yeah.
0 is just a slim corner of your Hilbert space, and 1 is your ready state, which is super large. Would that count as a measurement apparatus as well? Perhaps it's just like a relabeling here, right?
No, I mean, sort of, you wouldn't build a measurement device like that in
Yeah,
practice.
exactly.
Yeah,
But when
exactly.
in
Yeah,
principle it counts as a measurement is the sort of question.
Yeah.
I see. And the final state after the entire process, it's still not the definite state, right? You rely on some state update at the end. So basically, you're talking.
Oh yeah. So I'm assuming that you update. You mean here?
Yes. So they're just parts of the final state, right? You rely on some finally measured outcome. So the dynamics itself doesn't give you the definite outcome.
Yeah, I mean, so what? No, the dynamics doesn't give me a definite outcome. So it just gives me the mixture of the definite outcomes, right? And so it's so whenever an outcome shows up, I mean, then I update my description.
Then why is it still sufficient to say it's a measurement model? Because it doesn't give you one outcome.
Yeah, so I mean, it's not my purpose here to actually decide what's going to be the outcome, right? Because I think it actually violates bare inequalities, right? I mean, it's not predefined somehow, right? So it's kind of, I don't want to actually, I mean, it's actually a feature. It's not a bug of the model to not be able to detect, I mean, to say what was the outcome. I'm not sure I understand. Is that what you're saying? It's like I should be able to say what outcome is going to happen?
Oh, I'm just saying that it might be an intuition that any measurement can give you a measurement outcome, right? One single
Yeah.
measurement outcome, but.
I mean, he's not
if you're-
trying to solve the measurement problem.
I see,
He's
I
just
see.
trying to say, when is it safe to assume that a measurement has occurred?
Yeah.
In the sense of like, you won't be able to observe any difference between
The statistics.
just the statistics.
I see.
Yeah.
That's fair.
Yeah, I think that's all I'm aiming at. So it's no more than that.
Sure. Yeah, Fernando, I think that we can wrap up here because we have like other meetings and lunch is getting.
Sure, sure.
Yeah,
Yeah.
but thank you. I think let's thank Fernando again.
Thank you very much, Chris, and
Yeah,
everyone
we
for
reconvene next week with Carlos, but Fernando, thank you very much
thank you,
for
Chris. Thank
opening
you.
our seminar series, and thank you.
Thank you. Cheers.